I've got to say I disagree fundamentally with that quote from Heisenberg that opens up this video and is at the start of chapter 6 of the notes. He's fairly scathing about the idea of visualization and scathing about Schrodinger's approach, which is known as wave mechanics, and it's what we've been doing since we started the quantum world. Matrix mechanics, which is what Heisenberg is referring to when he talks about matrix elements, is a more general form of quantum mechanics, but it's equivalent to wave mechanics. I'm very much a wave mechanics person, as I intimated or said directly at the end of the last video. It's difficult to be a scanning probe microscopist and see the type of images I've been talking about in the last video and throughout the module to a certain extent, and not get drawn to that wave mechanics mindset. And moreover, from a teaching perspective, what I really like about the wave mechanics perspective is that it's showing you that quantum mechanics isn't this entirely otherworldly, ethereal, we're never going to understand this, it's all too complicated, you've just got to bury yourself in the maths because there's no way of sort of visualizing. There really is. We can't visualize everything, including in particular the wave function, or as we're about to see, the state vector. But we can certainly visualize a lot of things like probability density, and we can see in real space before us, you know, the results of manipulating probability density, setting up different confining potentials, just as I described in the last video. So, and we see that we've got these incredible parallels with waves on a quantum level and waves in the big bad world around us. And I think we do the subject, quantum mechanics and physics in general, a massive disservice if we don't point out those links. It's also educationally much better for you to see those links with wave mechanics and wave phenomena throughout the macroscopic world. But Heisenberg's approach, the matrix mechanics approach, actually it's unfair to call it Heisenberg's approach because Max Born and colleagues really laid the groundwork, did the foundational work for matrix mechanics, is more general. It's much more mathematically abstract from one perspective, though I'm going to be at pains again to try and make that mathematical abstraction concrete. And ultimately, what matrix mechanics is really dealing with a spreadsheet. Okay, it's an infinite dimensional spreadsheet, but it's all just rows and columns and matrices of numbers. That's what we're dealing with. And you've been dealing with that, thinking along those lines. It's why I've been so keen to embed coding throughout the quantum world. You've been thinking of a function as a list of numbers because that's all a function is. So on a computer, it's a discrete list of numbers. On analytical maths, it's a continuous list of numbers. But it's still a list of numbers. And that's really what matrix mechanics is all about, manipulating those numbers and not getting stuck on a particular form of representation of the quantum state. We've touched on this. No, not just touched on this. We've gone into this in quite some depth. In that, we've already seen that in the position representation, we can represent a wave function in a number of ways. Here's one, where these are eigenfunctions of the Hamiltonian, and these are the coefficients associated with that, with those eigenfunctions. And we've seen that the probability of measuring the eigenvalue associated with this eigenfunction is given by, which is the Born rule, Born interpretation. That's one representation. Here's another. Let's do it like this. So this is one basis set. Our eigenfunctions of the Hamiltonian give us one basis from which we can build up our wave function. delta functions give us another basis from which we can build up our wave function. And if you don't see what's going on here, now I covered this in the synchronous session, last synchronous session, but let me just get it down on video as well, or in one of the asynchronous videos as well. So let's say we've got a wave function that looks like this. What is going on with this integral? And why can we represent a wave function along these lines? So let's say we've got a wave function that looks like that. What is this doing? Well, what this is doing is, all it's doing is breaking the wave function down. I'll space out these delta functions a little bit more so you can see them. Doing an infinitesimal spacing on a blackboard is quite difficult. But what's happening here is that we are breaking the wave function down into a set of delta functions. And at each point, what we have is the value of the wave function at that point x0. And then if we integrate this up, and remember that the area under each one of these delta functions, and I should really draw them like that, is 1. So when we take this integral, then what we're basically going to do, let's get rid of that, is we're basically going to map out a wave function. That's what this integral is doing. And that's given us our psi x. Core thing there is one basis set, another basis set, and we can write another basis set. So we can write this as a Fourier integral, where our basis is now, and this tells us so as a Fourier integral, where this is now our basis. We've now got a plane wave basis. And the Fourier transform tells us the mixture of those basis functions we need to get this. The coefficients here, which are discrete, tell us the mixture of our basis that we need to get our position representation of the wave function. So that's the position representation. We can also, we've seen other representations where we've seen one other key representation, is if that's our wave function in x, well, it's already here. So it's a wave function represented in terms of k, spatial frequency. P is equal to hk, so this is in essence our momentum representation. So we're translating between two representations here. One in terms of position, one in terms of momentum, back and forth. And quite a few of the interactive figures include both those representations, so you can see them evolve, particularly with the Gaussian wave packet, motion and tunneling. I've deliberately plotted both the position representation and the momentum representation. And remember that the position representation, when we Fourier transform to get the representation in terms of spatial frequency, in terms of momentum, those are equivalent. To the point where if this one's normalized in terms of position, it's going to be normalized in terms of momentum, in terms of k. So let's say this is the modulus squared of our wave function in terms of the position representation, and it's Gaussian. That's meant to be up there. And we Fourier transform this, and we get the representation in momentum space, and we're also going to plot this in terms of the modulus squared. Now, you know, if we want to work out the probability of finding the particle, say with positive x values, then we integrate under here. That will give us the probability. Similarly, over here, if we want to know the probability of finding the particle with positive k values, positive momentum, then we integrate under here. This is our probability density in position. This is our probability density in spatial frequency, and because p is equal to h bar k, this is our probability density in terms of momentum. Matrix mechanics takes that to an entirely new level and doesn't force us, doesn't bias us towards one representation or the other. But I will stress again that wave mechanics and matrix mechanics have got their same goals and they're entirely equivalent. Matrix mechanics is more general. There's a certain arrogance out there amongst the more arrogant breed of physicists that, well, if you're doing matrix mechanics, you're doing proper grown-up quantum mechanics. If you're doing wave mechanics, you're doing a lesser form of quantum mechanics. I have no time at all for that. Some problems are better treated in terms of matrix mechanics. Actually, next semester you'll go on and think about spin, but some problems are most definitely better treated in terms of wave mechanics. So just because it's more mathematically complicated doesn't make it better physics. But matrix mechanics certainly has its benefits in terms of this generality and getting rid of thinking about a particular representation. It's much like if you've got a vector, you know, and you've done classical fields enough over this semester to know this well by now, we can represent that vector in terms of Cartesian coordinates or polar coordinates or cylindrical coordinates. And you know, if it's representing a physical quantity like velocity, velocity is velocity is velocity. It doesn't matter how we represent it. The map is not the territory. It's not like when you watch a ball move and somebody's walking across the car park or whatever. It's not like there's a big vector over their head pointing in a particular direction. That's our representation. And we shouldn't mix up the representation with the reality. So with matrix mechanics, what we're dealing with are lists of numbers. I can't stress that enough. And a core part of matrix mechanics is that we stop thinking in terms of functions and we start thinking in terms of vectors. That might seem strange, but as I'm about to show you, they're equivalent. We can think in terms of functions, think in terms of vectors, wave mechanics, matrix mechanics. The two are equivalent. It's just different perspectives on the same thing. So let's go through just where we get that equivalence between functions and vectors. And let's start right from scratch. Let's write down a vector. Where I've chosen the standard unit vectors I, j, and k. So we make up any direction in terms of a linear combination of those basis vectors. So we have a vector that is a linear combination of its basis vectors with certain coefficients that tell us how much of each basis vector we need to get the vector that we've defined, to get this vector, f. Doesn't that sound very similar to we have a function and we can represent that function in terms of a linear combination of basis functions, and the coefficients tell us how much of each of those basis functions we need in our wave function? Exactly the same idea. Exactly. But we can go a lot further. First of all, how would we represent this on a computer? Well, what we'd have is a vector and I've deliberately written it as a row vector. We're going to see column vectors too, which looks like that. Simple as that. Notice just the coefficients. We've taken the basis set for granted. We've represented that just in terms of the numbers we need. Let's say if this is our x direction, we've got a unit vector in that direction. 1. We've got 1i, but we're not telling the computer it's ijk. We're taking that basis set for granted. This is our representation. It's a list of numbers. Fairly short list because we've only got 3 dimensions, but it's still just a list of numbers. Now, we've used the term orthogonal and orthonormal throughout this module. And you've also come across the term orthogonal, of course, when it comes to vectors. So if we have now defined another vector, g, that's just going to be g1, and we're working in the same basis set, and these are unit vectors, then what we have is that. And let's say we or vector G is, oh, let's make it orthogonal. Let's say it's in that direction. List of numbers. Again, we've just got coefficients that tell us how much of each basis vector we need. Just as we had in terms of representing the wave function like this. Coefficients that told us how much of our basis functions. Coefficients that tell us how much of our basis vectors we need. Same concept, identically the same. When it comes to matrix multiplication, we can only multiply rows by columns. It makes literally no mathematical sense to multiply two row vectors together. We have to multiply rows by columns. So what we need to do here to get the dot product of these two is we take this one and we take the transpose of this. So what we're doing is, and let's be clear, f dot g. So let's get our dot product. 1 by 0 is 0, 0 by 1 is 0, 0 by 0 is 0. Gives us a scalar, 0. Which is good, because those vectors are orthogonal. Therefore, the dot product, or to use the more general term, inner product. So a dot product in this case is that. So let's do that on a computer. Let's just write that code straightforwardly on a computer. Let's do that. Okay, nice empty Python window. So let's write a really straightforward, simple piece of code. Trusty old NumPy. And we're going to set up a row vector. And let's call it f, just as we had. And let's do that example we have on the board. Now, there is an important aspect of this to tell Python that it's a row vector, hence the 2 square brackets either side. That forces Python to recognize that this is a row vector. And you can see it's just 1, 0, 0, just a list of numbers as we had on the board. And now let's define the other vector. Looks like that. I'm going to make a deliberate error here, just to show you what happens. So if we now try to take the dot product of those, which we can do with NumPy like that, of those two vectors, and let's just print. Oh, a couple of you have asked me about the underscores I use in the code. The underscores don't mean anything. They're just there to space out the words because we can't have spaces in variable names. It's just to make the code easier to read. There's no special significance of those underscores. They don't do anything. It's just basically aesthetics. So let's run that. And it comes up with an error because what we've tried to do is multiply two or get the dot product of two row vectors, and Python screamed, no, I can't do that. So what we need to do, just as I said on the board, is we need to get the transpose, and let's do that. Call the transpose of G that, and then it's as simple as that, and then we get the dot product of, and it looks like that, and let's run that. And now it returns 0, which it should. Now, why is it returning that in a strange format? Well, the reason it's returning that in a strange format is because by default it returns it as a scalar disguised as an array, which is a bit unfortunate, I will admit. But what we can do is just tell it, look, it's not an array. There's only one value in there, and that's the 0th value. There's only one value. So what we can do is just print that out like that. Don't get hung up on that. That's just a question of how Python represents its scalar dot product, inner product, whatever you want to call it. But the value, as you can see, is 0, which it should be. Let's just test that. Let's take another vector, which is not orthogonal to that. Let's run and see what we get. So everything's good, everything works. So very simple piece of code just to show you key aspects in terms of row vectors and column vectors. Now you know all this, but I'm just revising this because when we move on to Dirac notation very, very soon, within the next minute or so, keep in mind that it's all about row vectors and column vectors and matrices. Just always keep that in mind, because otherwise you will get buried in the mathematical abstraction. Right, back to the blackboard. Now what we're going to do is extend that idea to not just 3 components and 3 basis vectors. Let's move that to n basis vectors. So we're moving to an n-dimensional space. So our dot product then becomes, I'll use the index m, and usually we talk about an n-dimensional space and we have a lowercase n. I'm just going to use an uppercase n, just to remove confusion. And a lot of you get confused about why is it m, why is it n, why is it l, etc. It's an index. You can label it whatever you like. And I do my best to try and not confuse you, but sometimes it's difficult. There are only certain number of symbols that we can use without causing some clashes. But here, this is just a number. So we'd have, that's our orthogonality condition. So we've got 3 dimensions. If n is equal to 3, it's just what we had. f1 by g1 plus f2 by g2 plus f3 by g3. That's the coefficients multiplied together. And if they're 0, then our vectors are orthogonal. But we can move that to n dimensions. So we could have 50 different basis vectors, or 100, or 1,000, or 10 million, or an infinite number. And what happens when we have an infinite number? Well, it's exactly the same idea as when we moved from Fourier series to Fourier transforms, where we're going from a discrete set of coefficients to a function. So instead of having a delta x or having discrete values, we have an infinitesimal change in our function. So what we'd have is, in the discrete case, m, what is our function? It's just a series of values, coefficients. So here we've got an n, 1, 2, 3, n, 6-dimensional. And gm would look the same. But they're just values. And if we increase the dimensionality of our space, and we keep increasing the dimensionality of our space, representing it in terms of more and more basis functions, until we get to the point where, when this goes to infinity, then what we have is no longer discrete coefficients, but a continuous function. And this summation becomes an integral. And now I'm going to choose x. We can choose whatever bloody variable we like, but I'm going to choose x just so it looks a little bit familiar. And there's our orthogonality condition for functions. So functions are just vectors in a higher dimensional space. I say just. I know that's a little bit of a mouthful, but it's a simple, relatively simple concept. Because what are we doing? Remember that we're saying that we can reduce our vector just to a list of its coefficients. How much I we need, how much j we need, how much k we need, or if we're in a higher dimension, how much of each of our basis functions, basis vectors we need to make up our final vector or our final function. This you will possibly recognize from before, except you've seen it in this form, with that taken as the complex conjugate. Why do we do that? Well, we want to ensure that when we get the dot product of a function with itself, we want to keep our normalization. We want to ensure that everything's normalized, so that's got to be equal to 1. And if it's a complex function, we need to take the complex conjugate for our orthogonality, orthonormality condition. But this overlap integral is identical in a higher dimensional space to the condition we have for the orthogonality of 2 vectors. So that in terms of a function space, in terms of thinking this in terms of functions, well, that overlap integral is telling us how similar those functions are, how much they overlap. The orthogonality condition, if you'll excuse the somewhat sloppy and not particularly mathematical language, tells us how much to the degree to which two vectors point in the same direction. So if they're orthogonal to each other, 0, but then as we bring them closer and closer, in terms of pointing in the same direction, if they're pointing in the same direction, then 1. That idea. So our orthogonality condition is our overlap integral. So there's this direct link between functions and vectors. Okay, we're now at the point where we can introduce Dirac notation. That's going to be the subject of the next video. I know some of you have been waiting for this with bated breath. Okay, see you in the next video.